This is the second part of Chapter 2, Essential Chemistry for Biology, and we're going to deal with electrons and bonds. So let's get started. In the first part, we talked about atoms and the atomic arrangements. So we had protons and neutrons in the atomic nucleus, and then we had electrons that were zooming around. Now think about that image from the previous presentation where we had these electrons form an electron cloud, and it was shown in yellow. Now if you take one of those yellow clouds, which has the protons and neutrons inside and the electrons zooming around, and you take a second one, basically as if they were something like a basketball, so you have two basketballs in your hands, and you bring those close together, then you realize that the surface that interacts is the outermost surface of this basketball, meaning that when you're looking at atoms and you're bringing atoms closely together, it is also the electron cloud that encounters the other atom. And so when you're working with these atoms, you're not actually working primarily with the protons and neutrons. Those are packaged tightly on the inside. No, what you're actually working with is the electrons and the electron clouds. So what the electrons do with each other, how they interact, that determines how atoms behave when they encounter other atoms. And this is something that we need to talk about. The outermost orbit of the atom is known as an electron shell. So you have these electrons zooming around, and as they zoom around, they form this electron cloud. It's a spherical surface area that they can zoom around on, and that is their electron shell. Now, I don't know why they call it a shell. It's sort of like a nutshell or perhaps like an eggshell. But if you consider that basketball example, if you look at the surface of a basketball, that would be the possible pathway for these electrons to zoom around. And so if you take that basketball and picture it and make it very, very tiny, and on the inside of it you have the protons and the neutrons, then around the surface area of that basketball is when the electrons would be able to orbit. Now it depends on what kind of atom you're looking at, what these electrons do and how many of these electrons there are. It turns out that one of the things you always want is an atom to be electrically neutral. So if you have, let's say, two protons in the nucleus, then you would end up with two electrons zooming around the outside, and therefore the two positives on the inside, on the protons, would cancel out electrically the two negatives, the electrons, and therefore you end up with a neutral atom. So if you're counting, then you would basically always have the same number of electrons as you would protons. Now it turns out, as we already heard, that the protons are what determines the position of an atom in the periodic table, because the protons ultimately provide this element with its properties. Well, it also gives this element the number of electrons that are going to zoom around, and there has to be a certain arrangement of these. Now imagine, just to make this a more straightforward concept for you, a ping pong ball. Now the ping pong ball is symbolic of the nucleus of this atom, and perhaps there's three protons in it and three neutrons, or maybe it's 6 protons and 6 neutrons. Whatever it is, that is the nucleus of this atom. Now you take this ping pong ball and place it inside a baseball. The baseball would give you one surface around which these electrons can ride. And so the baseball is one of these electron shells. If you have a larger kind of atom, then you may have additional shells On top of that baseball shell, maybe you take that baseball and ping pong ball assembly and place them inside a basketball. Well, the basketball is then giving you the next layer of electron surface, another electron shell, and now you place that whole assembly into a beach ball and you have another one. And so just as this example goes, we have the nucleus in the middle, we have one shell, that's the baseball, we have a second shell, that's the basketball, and we have a third shell, that's the beach ball. And so we can accommodate quite a few electrons, and this atom will be held together by these electrons and by these multiple layers of electrons, and so that way everything stays together. Now each of the balls represents this shell on which the electrons can travel. Now let's take a closer look at how this might work. Here are those four elements that we talked about initially. We have first up hydrogen. And as you can see, hydrogen is a fairly simple atom. In fact, it is the most simple atom. All it has in the middle here is one proton. That's the positive charge. And in order to cover up that positive charge, we need a negative charge zooming around on the outside. That's given to us by one electron. So here we have one electron, one proton. This is the smallest atom. It has an atomic number of 1 because it only has one proton. And this particular atom only has one shell needed to accommodate electrons. The next one of these is carbon. And carbon is a little bit different than the hydrogen because carbon, first of all, has quite a few more things inside of the nucleus. In fact, if you were to count them, we would be able to count 6 protons. That is the atomic number of carbon. Then you would also have 6 neutrons. And those 6 neutrons and the 6 protons make an atomic number, make a mass number of 12. So the mass number of carbon is 12. In addition, because we have 6 protons, we're going to have 6 electrons so that this atom can remain neutral. Well, it turns out that the first shell can only hold 2. 1, 2. It can only hold 2 electrons because it is simply too small. It does not have a large enough diameter to hold more than 2 of these very fast moving energy-rich electrons. And so what we have to do in this case is expand the atom. This, remember, in the middle, that's your ping pong ball. Next one out, this one here, that would be your baseball. And then the next one out beyond that, that's going to be your basketball. So we have a second shell. And on this shell, we have electrons number 3, 4, 5, and 6. And so together, we cover up the protons in the nucleus with 6 different electrons on the outside. And when we look at this by way of accounting, we have 2 of these electrons on the innermost shell, and that's all that shell can handle. And then beyond that, we have 4 on the second shell. In this case, that is the outermost shell of the carbon atom. And it has 4, but it can actually hold more. See, here's an empty place, here's an empty place, here's an empty place, and there's an empty place for a total of possible 8 electrons. So the outermost shell in these atoms can actually hold 8 electrons. Now we go on to the next one, we go to nitrogen, and you can see here a little bit of a difference. It's got an atomic number of 7, which means it has 7 protons, and it's going to have 7 electrons. 1, 2 on the inner shell, 1, 2, 3, 4, 5 on the outer shell. 5 on the outer shell, and 2 on the inner shell. That makes 7, so we're covering up those protons for a neutral charge. And then lastly, we do the same thing with oxygen. There, the number is 8, and so the numbers are as before. 8 protons, 8 electrons, 2 of these electrons on the inner shell, and 6 on the outer shell. Now, as these atoms grow, obviously, these numbers may change. And once you get to 8, once you fill this outer shell, then you have to add a shell of electrons to go beyond that. So if you look at an atomic number of 11, well, in that case, you'd have 2 electrons on the innermost of these shells, 8 on the next one, and 1 on the one after that. Now, this will become important in a minute when we talk about bonds. Chemical reactions actually happen by the change in electron configurations. That makes sense if you think about how atoms encounter each other. One atom has electrons zooming around its outside. The next atom has electrons zooming around its side. When you bring those close together, of course, these electrons are going to be running into each other. And as they run into each other, it makes chemical bonding possible. There are different types of chemical bonds that we'll look at, and they all add up to a way of combining these atoms to make larger substances, and we call those molecules. Now, atoms can give up electrons, or they can gain electrons depending on their electron shell configuration. And so if you look at these first several electron shells, you realize 2 are possible on the innermost shell. Then, as we just saw, 8 on the second shell. Then, because it's now getting a bigger surface area, 18, and then 32. So 2 electrons, 8, 18, 32. And it turns out, this is one of those law of nature kinds of things, that each atom would like to fill its outermost shell. They would like to have its outermost shell filled. Well, what does that mean? If you have 7 electrons on the outermost shell, you really want 8. What do? Well, the easiest thing is to add 1. So you're going to have to find an electron from someplace to add to your 7. And then you'd be nice and happy and stable, and perhaps it will help the other atom as well. And so when we're going to look at bonding, the movement of electrons is going to be something we're going to be very interested in. Depending on what kind of exchange is going on, it will eventually result in these atoms doing something together, staying close together, and that means that they formed a chemical bond. Some of these chemical bonds are very strong, some are fairly weak, some are easily reversed, some of them you basically can't reverse at all unless you put a lot of energy into it. So chemical bonding is a very diverse type of study. The first type of these bonds is called an ionic bond. An ionic bond is something that happens when an atom changes the number of electrons it would normally have. Now, the way it can change electrons is either by picking one up, which would give it a more negative charge, or by giving one away, which would give it a more positive charge. Either way, however the atom takes on this electric charge, it becomes ionized. And this word ion basically means that some kind of electric charge is now on this atom. And so the ionic bonds that can form between these ions, those are the things that occur because of the movement of electrons and because the electric charge changes. Let's take a look at these diagrams. Here we have a sodium atom. The sodium atom, if you go back to the periodic table, is something that is a pretty standard small atom. It has a certain number of protons and neutrons, and it has the electrons zooming around it, and these electrons are creating a neutral atom. Now, when you look carefully at this, you can see how many of these electrons there are. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the sodium atom has 11 electrons. I'm drawing this as an E for electron and a negative sign because it's a negative charge. Well, think about this for a minute. If the sodium atom has 11 electrons, how many protons would it have? Think about it. A proton is positively charged, and if we're going to have a neutral atom, then you have to have 11 protons, right? 11 negative charges canceled out by 11 positive charges. So that's how you can figure some of this out. Chlorine is a little bit different. Chlorine also has 3 shells, 1, 2, 3. It has 2 electrons on the inner shell, 8 on the next, and 7 on the outermost. Now let's think about this for a minute. In sodium, you have 1 electron that's on the outermost shell. Here you have 7 electrons on the outermost shell. As I mentioned a minute ago, both of these atoms would rather have their outermost shell filled. Now, in the case of sodium, that means it would need to gain 7 or lose 1. Well, losing 1 is a lot easier than gaining 7. Losing 1 is 1 transaction, gaining 7 could be as many as 7 transactions. And so nature works often with the easiest pathway, and that would be, in this case, to lose it. And here's what happens. So the sodium sends its electron over here to chlorine, and the chlorine atom therefore fills its outermost shell. Now that's really good because that way, for both of these atoms, the outermost shells are complete. If you look at the numbers now, there's an outer shell with 8, and there's an outer shell with 8. But, notice here, because sodium gave away one of its negative charges, it is now an ion, positive charge. Because chlorine accepted one, it is also an ion with a negative charge. Well, the positive and the negative opposites attract, and so now after this transfer of an electron has been completed, they form something called table salt, sodium chloride. Think about what this means. All you did was move 1 electron. That is a very small particle. It essentially has no mass. And you just shifted it from one of these shells to another. So it's the tiniest change in configuration, but it has a huge effect. Remember, this thing here was a metal. This thing here was a gas. And now that we've done this little exchange, this turns out to be a salt. What a difference. Who would have thunk it? This is the kind of thing that is an emergent property. We don't really know what happens when we exchange these or move them until we do it. So that's an example of an ionic bond. The second kind of bond that we're going to look at is one that happens when electrons aren't moved and left, but where electrons are shared. Now, what happens here is you're not forming ions. So what this means is that the electrons are still configured with their original atom, but they're now being shared. And here's how some of this sharing might work. So over here, for example, you have a hydrogen atom, another hydrogen atom, and on the outermost shell of each is 1 electron. But these electrons now are being shared. So electron 1 goes around like this, and around like that, and around like this, and around like that. Meanwhile, the other electron, remember, there's one from each of these atoms, the other one does the same thing. And so they're being shared. They're being equally shared, they zoom around, and this is a covalent bond. When we look at the structure of these, you'll find that we take a sign like this, and this sign, this actual stick, if you will, this connection, this line, is what indicates a single bond. Now, when you looked at this sodium chloride in the previous slide, there was no bond. It was not outlined by a line or anything. It was just sodium chloride. And this indicates in chemistry that this is a tight bond here. Now, in this case, if we're drawing it like a structural formula, you'd actually have a bond like this. That line indicates a bond. In this case, with the oxygen, you have 2 lines. That's a double bond, and it means that 2 electrons are being shared. In this case, you have 6 on the outer shell. Well, 2 of those 6 are being shared with the other oxygen. So that one has 6, and it's sharing 2. Well, that means it's going to have 8. It'll be happy. On the other side, it will also share with the other one. So these electrons are doing double duty, and you have 6 plus 2 on that side. Again, electrons being shared. And then you can extend this whole thing into having multiple atoms do this. So in this case, carbon with 4 different hydrogen atoms. 4 electrons being shared from the hydrogen, 4 electrons being shared from the carbon. That means carbon feels as if it has 8 of these electrons available. So that means for carbon, it feels as if it has its outer shell full. That makes it very happy. Likewise, each of these hydrogen atoms is going to be able to share 1 of the electrons from the carbon, and each of the hydrogen atoms feels as if it has 2. And so its outermost shell is filled, and it is very happy as well. And this is how we form covalent bonds. So those are the most common kinds of things in terms of bonding that we'll encounter. And for our purposes, when we're dealing with the molecules of life, covalent bonding is going to be the most important type of bonding to become familiar with. This is the end of the second part of Chapter 2. The next presentation is going to be dealing with water, and that's the third part.